All right, guys, so we have a lot to do today, so let's get back into it. So we did, last time we talked about this guy here.
Oh, yeah.
And what does that create? If we use that, what does it create? Good. It creates a confidence interval. I like it. And which part of that confidence interval reflects how confident we want to be?
In between?
Or which one do I find based on how confident I want to be? Let me say it that way. If I tell you I want a 99% confidence interval, which piece of this will you be able to get? Z. So this is the Z, tells me how far out I'm going to go. So if I want to be 99% confident, this makes too much sense. It's almost scary. If I want to be 99% confident that I catch a certain thing, I'm going to catch 99% of the stuff. So that's why I like the fish idea. There's a certain fish in there I want, right? I bit my finger off years ago. I want it. Yeah. So if I want to be 99% sure I caught that damn fish, I'm going to catch 99% of the fish in that lake. You with me? Yeah. It's kind of like a boiled down version of Ahab. A little stumbling. So I'm going to have, So if I go out far enough, and of course what controls distance in statistics is the Z-score. Z-scores are how far, how many standard deviations out. Okay, good. So that's the connection between how confident I want to be and what changes in this equation to reflect that. All right. Okay, so let's remind ourselves. Can somebody help me out? What's the Z-score for 98% confidence? So again, how would that look like visually? Yeah, 98% would be where on the picture? In the middle. I want to go out so far. I want to catch 98%.
2.05.
Be careful now. If you look up 0.98 in the chart, if you look that up, you're not going to get the right answer. Because that would be the Z-score that has 98% below it. Does this Z-score here have 98% below it?
No.
No, it's missing that much, right? Yeah. So what's this Z-score have below it?
0.05. Or 0.1.
0.01, is that cool? If there's 98% inside, there must be 2% outside. There must be 1% on that side. Right, because of the symmetry. So look up 0.01. Say again, sir? Yeah, keep going with it. 2.3. Get closer. No? Should be 2.33. So those of you playing along, if you look at your Z-score charts, what's the closest I can get to 1%?
Negative 2.33.
Yeah, I get 0.01. Where am I at? 0.0099. That's the closest I could possibly get to 1%. So that's going to be 2.33. So there's negative 233? Positive 233. Now why is the plus and minus in this case, what I just looked up, not even matter? Because it's built into the equation, right? That's why that plus or minus is there, because the equation has built into it the fact that I got to go up and down so much to catch. All right, how we know so far? So see, it's almost scary how much sense this makes.
Wow.
Some of you guys are like, no, actually, I'm not scared at all. It makes no sense at all. All right, hopefully not too many people like that. So these problems, let them be easy. They have to give you basically every damn thing. They have to give you everything. So if I said, remembering what we just did, if I said there's I take 48 people, and I find an average of 1.98 pounds of candy that they got. And I know the standard deviation of candy is what you got, Jeff? 8.4. Find the 90% confidence interval. Yes.
That was in the homework though. It didn't give you the standard deviation.
Oh yeah, I did it.
Yeah.
No, so for 7.3, are you talking about 7.3?
No, I'm talking about 72.
Well, 7.2 is for p hat and q hat.
Okay.
Yeah. So I start here. I start with 7.3 kind of stuff, and there's still part of 7.3 we got to talk about. 7.2, they don't have to give me the standard deviation.
Yeah.
Because 7.2 is this guy we talked about last time. We make the standard deviation. All they got to tell me is
That's
actually
the equation for standard deviation?
that's
For
7.2.
7.2?
Yeah.
Okay.
So effectively, this becomes our standard deviation.
Oh.
We'll see that again in chapter 8. When we're talking about percentages and we're talking about z-scores with them. That's going to be kind of our stand-in standard deviation. I don't know if you remember, it's been a week, but we derived that formula from something much like this, using square root of NPQ and all that kind of stuff for binomial. But how do I do this? What if they not told me? What's the only thing I don't know that I need to know? Yeah, they didn't tell me the z-score, but they told me it's 98%, and we just figured out z was
Negative
2.33. Let go of the negative. That's the one we found, but who cares? They got two z-scores, one's positive, one's negative. When I say what's the z-score, you just tell me 2.33. The plus or minus is built in. Okay, maybe. I mean, let this be a semi-decently easy mathematical problem to do. The concepts behind it are not that terrible, but they're certainly worse. This is not bad. This is just plug and chug. They got to give me the mean. 1.98, give or take. What goes here? 2.33. That's how far out I have to go to catch this much stuff. So start at the mean, go up and down this many standard deviations. So that'll be 0.84 divided by square root of 48. Because there are 48 people that we picked. And of course, the suggestion I made was for you to first calculate what?
The error.
The error. I love it. So there's the error. That's how much I think I'm off by. That's this, give or take that. It makes sense. It's a good name for it. It's how much we think we're off. So somebody help me out. What's that error? Yeah, it's going to be small, right? It's a very tiny standard deviation, and then I'm dividing by almost 7, right? So it's going to get even tinier. And multiply that. 12. Yeah, 0.2 something sounds right. Okay. 1.98, give or take 0.2. Do it one more time. 8.2. All right, so last little piece here that we got to remember is you need to write to me an explanation of what you just found. My statistics is all about the concept behind what formulas you use, and then at the end, what the hell did you just do? It's not good enough to tell me 7. Oh, well, what's it mean? What's 7 what? What the hell? So how do I, first off, what are the limits of my interval here? So 1.98 minus this. Bless you. Thank you. You get what? You get 1.698 to 2.262. And then how do I say this at the end? The little statement I have to make. Yeah, good. We are 98% confident that the interval 1.698 pounds to 2.262 pounds contains what? The true mean candy weight. Right. If you got to do a stats problem, it might as well be about true mean candy weight. It sounds weird if you say that. True mean candy weight. True mean candy weight. Okay, cool. Does that make some sense? Even if you completely don't understand the concept, which is a horrible place to be, but even if this is still just a plug and chug, the one thing you really sort of have to understand is how the hell to get that. It's the one thing they're not going to tell you. They're going to give you a way to find it. Where'd it go? Where'd it go? There it is. Yeah.
So all that's 7.3.
Yeah, this is part of 7.3. This is not all of 7.3.
Okay.
If you have the old edition, they have 7.3 and 7.4. The new edition, they put 7.3 and 7.4 together. This is the part of 7.3 where I know this. The other part of 7.3 is what if I don't know that? So maybe it's good. Let me do this.
P-hat.
Now I've just said that. Let me kind of go in that direction, and then we'll come back and do the P-hat, Q-hat stuff. You kind of with me? Because that stuff, I even have to know less for that one. It's kind of nice. All right. Okay. All right. So we kind of got into this whole thing by saying, normally I don't know this. I have to use this. And then I want to kind of have a feel for, well, where is this? How close is my sample to this? I want to get, that's the idea behind the confidence interval, is to say, I'm 95% or 98%, whatever, sure that the real mean is somewhere in there, that this one contains it, right? So it gives me a rough idea of where that is. So if I had I took a sample of people from LA, and I took a sample of people from San Diego, and I said, okay, in LA, this many people, this percentage of people want the Chargers to move there, and this percentage of people, after yesterday, anyway, all right, in San Diego, before yesterday, this percentage of people would be okay with it moving there. Is it possible that the same percentage of people in LA and San Diego, that's kind of a tricky question. According to what we've discovered, does it look like the same percentage of people? It could be the same in both cities.
No.
No, because the lowest this could be is 71, the highest that could be is 48, right? So that's one immediate use for confidence. Now behind that is a whole statement of the difference between these two is statistically significant. Say that, is statistically significant because they don't overlap. If they did overlap, then they could be the same, and then it's not a statistically significant difference. A little bit later today, we're going to be looking at how the males are doing in this class versus the females and making confidence intervals and seeing if anybody is statistically significantly different from the others. Oh, yeah. I should say, you will be. I'll just be watching you. All right.
Wait.
Sounds creepy. Okay. So that's kind of like what you can do with confidence intervals. So we had the thing where I started with this idea, and that's where we built. We said we normally don't know this, but going along with that, we normally don't know this either. Because what's this represent?
Standard deviation.
Of the population. So it should make sense that if I normally don't know the mean of my population, I more than likely don't know the standard deviation either. In fact, the best I could do here is x bar, and normally the best I could do there is, well, no, instead of sigma, s. Cool. And then we can build up the formula just like before, right? Let me stop there for a second. You guys kind of with me?
S is the standard deviation of the
Sample. Yeah. Okay. S. Sample. Yeah. So sample is going to be R letters, and population is going to be Greek letters. Yeah. Okay. So if I know this, then I can use z-scores. Now here's the thing. If I had a confidence interval, in fact, let's look at this one. If this was built assuming I knew the sigma, what would have to happen if I wanted to cover my ass for the fact that I didn't know sigma, I only knew S. And why is S? Why do I say only know S? Any sample I take, how much do I trust that S? I trust it more if my sample is bigger. I love it, but I still never trust it 100%, do I? Until I get the whole damn population in there. Then I trust it, right? So I never quite trust S fully. So if this was made thinking that I had this, when I really don't, to be more conservative, to cover my ass more, what should I do with this? What should happen with this to cover me? Should it get bigger or smaller?
bigger.
It should get bigger to cover me. If there's a part of my stuff that I don't know, then my interval needs to be bigger. It's got to catch more stuff. So the fish, if I think they swim this much, but I'm not sure, I'm going to throw a net out a little bit bigger. to cover for the fact that I don't know. Now, if I knew for sure they only swam out this far, I'm just going to catch a net and throw a net that far out. Why have the chance it's going to catch on something and snag and break? Right? I'm just going to do that far. All right, you guys kind of with me here? So, what we've done, you're gonna so desperately love this. All right, let me introduce it this way. There's a guy that worked at the Guinness Brewery. Do we have anybody here that likes to partake of Guinness? Anybody? All right, it got me through grad school. All right. You go with the teachers, get them on Guinness, and they start kind of letting certain things slip about the next test. This is not a story. So there's a guy that worked at the Guinness factory, and what he wanted to do was he's doing a study about the effects of different kinds of barley on what they're making. And there's kind of an urban legend about why he chose a pseudonym, but it's known that this guy did it. This guy named Gossett. So he didn't have this. He only had this, and he knew that there was a problem with that. He knew it wasn't really being honest doing with z-scores. So he said, okay, let me develop something else. Let me develop a distribution that's more true. A distribution that's true for S and not sigma. So the bigger n gets, the closer this guy should get to a z distribution. Let me say that again. This is kind of like we know. The bigger n gets, the more I trust this, the less I need some different thing. The more it should look like a z-score distribution. And let me show you this real quick. Let me at least get this waking up. I want to show you a picture of it so you can see what I'm talking about. At the end of the day, as this thing is warming up, if I have 98% confidence, we just figured out that this is going to be 2.33. Right? The thing that he developed is called the student's T distribution. And I think the T is because they called it test distribution. It's called the student's test. So student was his pseudonym. Student was his the name he used when he turned it in. Some people think it's because Guinness didn't want him publishing this study because it was going to be bad for them. So he wanted to do it under a different name so he wouldn't get fired because he enjoyed Free Sample Tuesday. Right? That part might not be true. But do you have any teachers that immediately discount? Okay, open. Immediately discount Wikipedia. Do you have anybody that's like that?
Yes.
I don't know how to say this diplomatically, but you can always start with Wikipedia and get the sources. I mean,
Exactly.
It's an awesome location for somebody who's already done all this work, getting all these sources together. Hell yeah, I'm going to go there. I'm not going to just take something straight from the page. That much you maybe can't trust all the time. But it's really good, too, for this kind of thing. I just want to show you. I like the one that's on Wikipedia. There you are. No, too close. Yeah. Well, this might be good. All right. So in blue is a normal curve. In red is the associated student's T distribution if the sample size is 1. So you can see how radically it's pretty different. It's much lower. It's got a lot more out here, right? You guys kind of with me?
Yeah.
So we're talking now about what he developed to cover his ass. Every score you get from his distribution is going to be a little bit bigger than this would be. And then why does that make sense? Because like we said, you'd want every confidence interval to be a little bit bigger to help cover your ass for the fact that you don't know something. You don't know the real standard deviation. And if n gets bigger, the only bad part about this close up is you don't see all, hello, that's different. Come back down here. All right. So here's n equals, oh yeah, here we go. So we'll have to talk about degrees of freedom here in a second. But basically this is for sample size of 2, 3, 4, 6, 11, and 31. So once you get about 30 or so, we kind of know this is true. I get really, now all these green ones are like, that's the one thing I don't like about it. The green one's like the previous picture where it was. You know what I mean? So you can kind of see the progression. Now they're basically lying right on top of each other. It's become normal. So we know that when your sample size gets bigger, everything gets better. If your sample size is small, you're like, oh, I really got to cover my ass for this. My z-score, and the score I'm going to use is going to be a lot bigger than the z. It's not going to be 2.33. It's going to maybe be 7 or something, right? To cover for the fact that you don't know much about the standard deviation. But the bigger my sample gets, the closer the distribution gets, and the closer that the scores here get to there. All right, so that's the idea behind it. Now, here's the first immediate consequence for you. And actually, before I get to this, let me explain what this is. Degrees of freedom. I think we've talked about this a little bit.
Sounds like a movie.
Degrees of Freedom, the movie.
Oh, man. It's going to be the lamest movie.
Christian Bale.
Good for you. Is that too old a reference? All right. Now watch this. Just let me ask you this. If I knew there were 4 numbers that average to be 10. Can anybody tell me anything about any individual number? If you can, that's really freaky because I'm not even thinking of any. I don't know what you're reading into.
One of them is 1.
Holy crap, no. I just decided not to do that. Do I know anything about the numbers at all?
There's 4.
I know something more important. The only way that 4 numbers could average to be 10 is if they add up to be 40. Because how do you find the average? You add them up and divide, in this case, by 4. So if the sum of my numbers divided by 4 is 10, then the sum of my numbers must be 40. So how much freedom do I have if I just want to make up a list of numbers, not using the number 1, that have an average of 10? When do I actually have to worry? So I'm just going to start 7, -3. Do I have to worry yet? No. I mean, is this an average of 10 going to be? I can force it to be, can't I? How many more can I do? But how many more can I do and not care? 1 more. So if I say this is 28, now this one has got to be the number that's going to actually make it work. So what kind of a sum do I have so far?
A positive number?
Careful, it's -3.
Oh, I mean, it's 30.
So 32, right? So what's it got to be to make it 40 total? 8. So now I know the average of these will be 10. It's a whole different kind of way to look at averages than you're used to. Does everybody kind of get the idea there? So the idea is almost too simple, but this is why we have this thing called degrees of freedom. If I have 4 numbers, how much of them am I free to just make up?
3.
3 of them. And then the last one's got to be the one that actually ties it together. So if I have a list of 11 things, the sample size is 11, degrees of freedom will be 10. So degrees of freedom, very simply, degrees of freedom is n minus 1.
Wow.
And that actually feeds into, do you remember what was sitting on the bottom of the standard deviation way back in chapter 3 for a sample? It was the sum of x minus mu squared divided, x minus x bar squared divided by n minus 1. Very intricately related to that fact there. Okay, so all that boils down to, in order to use the chart I'm about to give you, that's based off of what this dude did, you have to first look at the degrees of freedom, because it's listed by degrees of freedom. So let me give this to you. I don't have samples of, yes, sorry. You guys are baby. Look under your chairs, there's nothing, except for what you put there.
Wednesday needs to be Guinness Day.
What's up?
Wednesday needs to be Guinness Day.
Wednesday is Guinness Day. BYOG. Oh, sure. BMSG, bring me some.
It's expensive. Yeah, it's expensive. That's why I really did it. Yeah, you gotta acquire taste for it.
That's the way I'm going to write that. Too many letters in the words confidence interval. All right. Now, what the hell? Uh-oh, it's going to be all freaky. Try this again. All right. So first thing to notice, one main feature of this thing is there's these two rows at the top. Whenever I make a confidence interval, how many tails do I make? Okay, good. So do you guys see how that relates to this?
Yeah.
In chapter 8, there will be times, and this is going to make immediate sense hopefully, if I wanted to test somebody's claim that my average grade is lower than what I thought, then it would be a one-tail test. I only care about that side. That's why this thing has one and two tail options. Confidence intervals will always be two tails. Right? Secondly, if you guys did your homework, you know what this little symbol means? Z alpha. So it's the area that's, yep. So if I have two tails, then I cut it in half. So notice if alpha was, so if I want a 98% confidence interval, alpha would be 2%, would be 0.02. But how much would be in one tail then?
0.01.
0.01. So if you look at two tails, 0.02. If you make a mistake and look at one tail, you're fine. It's going to be 1% in it. So they both relate to the same situation. You guys understand? So if I want a 98%, two tails is going to have 2%. One tail is going to have 1%. Either way I look at it, I end up in the same column. All right, maybe. Okay. So if I had, let's try one example together. If I had a sample of, what you got, Jeff? 37. And I want the 99% confidence interval. Do I have to tell you it's normally distributed?
No,
Why not?
because it's over 37.
Yeah, so I know my sampling, I know the picture that has all the sample means on it will be normal. Now the sample I pick doesn't have to be normal. The distribution of all samples will be normal. That's what that means. So if n is 37, what's the degrees of freedom? 36. And I can't remember, this guy has 36 on it. Huh?
Yes.
Yes, good. That's always useful. So 36, and I want to be 99% confident. So how much is in two tails? Yeah, one tail would have 0.005. Two tails, of course, would have 1%. Right, if there's 99% inside, there must be 1% out in the tail. So if I look at 1% in two tails and go all the way down to 36, that would be the score I use. 2. Where'd it go? 7.1, I think. So degrees of freedom is 37 minus 1 is 36. The t-score, oh yeah, the t-score I would use would be 2.791. 19. Now go back to the little baby chart and tell me, what would the z-score be if this was actually, so here I know S. What if I knew sigma? What z-score could I use? What would the z-score be for a 99% confidence interval? 2.575. And of course I had to pick the one that this is not quite the same. That's actually rounded, sorted the wrong way. Look at the very bottom, and remember what we said. The bigger n gets, the more that this stuff should get closer to z's. And look what happens. As n gets bigger, what happens to my t-scores? They get closer and closer and closer.
99%.
So look at all these. Do any of these look familiar?
Yeah.
2.33, we just did that one. That's for 98% confidence, right? It's 1.9, 1.645, we've seen that a few times. Not this one too much, it's a little bit low. Not many people would go there. Oh well, they just put it there in case you're that kind of person. So basically, what lives at the bottom of this sheet? Z-scores. So sometimes we're going to go to the t-score chart to look at z-scores. People always freak out. There's always somebody who's like, no, man, what the hell? This is t-score. Because at the very bottom live the z-scores. All right, maybe. Much better than that little baby chart they gave us. This has a lot more values on the bottom, right? All right, let's try another one. So this does not change the fundamental idea. What do I have to know before I can use z-scores or t-scores in this formula? What do I have to know is true? Distribution is normal, or at least normal enough, right? So either they tell me it's normal, or sample size is more than 30, right? So if I said S is known, population looks skewed, but N is 97. And I want a 98% confidence interval. Would I use Z or T?
T.
Why T?
Because
It's not over.
Beautiful. T-scores were invented to cover your ass for when you only know S. You don't know sigma. Period. So if I only know S, I sure as all hell cannot use a Z-score. I don't care if it's normal. I don't care if the sample size is tremendously huge. I don't care. I got to use a T-score. So that is the fundamental test you do. You got to know it's normal. So how do I know it's normal here? Yeah, so I got to know it's normal to do any damn thing. If it's not normal, you can legally just say, I don't know if you screwed this problem up, Jeff, but I can't do shit. And then go to the next one, right? Maybe to cover your ass, you should do it anyway, in case you're wrong somewhere. But so either I got to tell you it's normal, or the sample size normal somehow. I told you it's normal, or the sample is bigger than 30. And then which one, T or Z, is all based on, do I know sigma? If I know sigma, it's Z. If I only know S, it's T. That's the quick check to see which one to use. Now here's the really beautiful thing. I don't know if any of you guys ever take me when I say this. I've already said this a few times about formulas on your formula sheet. They're notes. So here we got the formula we already know. What do you think the formula is like for a t-score? Instead of a Z,
T.
there's a T. Instead of a sigma.
S.
So, I mean, there's a freaking note on your formula sheets. I can't do shit about it. It's a formula. But when do I use Z? Oh, when I know sigma. When do I use T? Oh, when I know S. Okay. All right, maybe. Let that be simple, please. But the fundamental idea of the T-scores always being bigger than the corresponding Z-scores, just because you got to cover your ass because there's something you don't know something about. You're not sure about the standard deviation. Blush. That's the part that is almost too scarily makes sense. Makes too much sense. Right? I don't know grammar. Give me some leeway on that. You talk good. All right, so here's what I want you guys to do. Here we go. So there are two parts to this. This side with the red writing, maybe don't look at that. That's from chapter 8. I'm just trying to save some paper, and I'm trying to be optimistic about how far we'll make it today. Just do the other side with no red writing.
It seems so simple, and I was trying to do the homework, and I was so lost. I don't understand.
What's that? This used to be simple?
No, like when you taught 7-2,
Yeah.
it seemed so simple, and then when I tried to do the homework, I was so lost.
Some of the questions
It was because of the standard deviation, huh? Yeah, it was after number 19. I couldn't figure out how to do standard deviation because they
It's
didn't
built
give it
into
to
the
you.
formula for 7-2. It's that square root of P hat Q out of right.
Because they
Don't worry, we'll come back to it when we're done with T-score stuff.
okay.
Yeah. Go back and do the P hat stuff.
I felt like they gave like 3 different equations in the book to do it, and none of them really told you how to do it. I don't know. Maybe I was just confused. I was so lost.
All right, guys, you can work on this alone or together.